Hammy here, coming to you with the first part of section 9.3, which we will begin to connect the ideas of Charles Darwin to another contemporary of the time, Gregor Mendel, and some laws of genetics, which the two never really connected their ideas at the time. But in the 20th century, scientists kind of started to put the two together. And so we want to look at what does evolution mean in the terms of genetics of populations. One of the first things we need to define is kind of the scale of evolution. There's two terms that are often used, microevolution and macroevolution. So micro meaning really small. If you look at the root word of the prefix, macro meaning big or large. Okay, so microevolution is referring to usually happens over shorter periods of time, and it's referring to smaller changes like gene frequencies within the gene pool of a population. Macroevolution is referring to larger changes, usually over geological time, so much longer in time. And it's often talking about leading to new species, so bigger changes. So you see over here like a change in color of the beetle might be microevolution, whereas when you look at kind of a bigger geological timescale look of the evolution of dinosaurs and birds and reptiles and stuff, that would be more of a macro type view. And the two are often sort of very related. Okay, next, one of the first things we needed to do is define what a population is. Okay, biologically speaking, or in ecology as well, a population is all of the same species that are living and interbreeding in kind of the same locale or same area. Okay, so that group of individuals in a certain spot. When we look at their gene pool, okay, that's all the genes and the alleles or allele frequencies within that population. We look to see if there's any changes happening. Okay, for example, if we look at, let's say, this allele down here, big A and little a, so it's just has two alleles, dominant and recessive. Let's say we have 100 individuals in the population. Let's say there's 50 that are homozygous dominant, 40 that are heterozygous, and 10 that are homozygous recessive. If we look at the allele frequencies, or how many alleles total are in the population, well, if you have two alleles for a gene and 100 individuals, 100 times 2, that's going to be 200 alleles. Okay, so we look at, well, you have 50 individuals that are homozygous dominant. So they have two big A's. So this column is going to be big A. This column is little a. So if you have 50 that are homozygous dominant, that's going to be 50, and they each have two alleles. That's going to be 100 big A's. Okay, 40 of them are heterozygous. So they're going to have one dominant, one recessive. So 40 times 1, that's going to be 40 big A's. And you look homozygous recessive, that would be 0 big A's. So we add 100, 140 big A's in the population. And then if we look over here, there's 50 of these. That's for little a. There's going to be no recessive alleles in those. Again, 40 is half dominant, half recessive. So we have 40. Okay, and then homozygous recessive, they have two little a's. So you have to take those 10 individuals, and they each have two alleles. So 10 times 2, that's 20. 40 plus 20 is 60 little a's. So that gives us our total 140 plus 160. That's going to give us our total of 200 alleles that we said over here. And now this would be the frequency. Okay, so big A, we would say big A, the frequency of the big A allele would be 140 out of 200, or about 70%, or about 0.7 or 0.70. Little a is going to be 60 out of 200, which is about 30%, or about 0.30. Okay, and again, notice you add those up, that equals 1 or 100%. Okay, so these would be the allele frequencies within the population. And to monitor evolution, we'll see if these frequencies, if any natural selection happens that will change these allele frequencies, and that could clue us in that they might be evolving. There are two scientists that independently came up with this theorem about allele frequencies and evolution of populations. G.H. Hardy here on the left and Wilhelm Weinberg on the right. And then we've sort of given them both credit, and we call it the Hardy-Weinberg Theorem. And what they said, in order for populations to not evolve, for populations to be in equilibrium. Remember, equals stay the same. So no evolution. Equilibrium equals no evolution. Okay. They said there has to be 5 things that need to be true. Number 1, no new mutations, because mutations could lead to new phenotypes, things that might give that creature an advantage. There's no migration, no immigration, things moving into a population, or emigration, things leaving, because they might bring in new alleles or certain alleles might leave. The population must be large to prevent sort of that random genetic drift, which can cause sort of random changes in the gene pool. So larger populations, like having a bigger sample size, kind of prevents a couple of them dying off and then a sudden huge shift in the gene frequencies. Mating needs to be random. We can't choose one individual over another based on their phenotypes, okay? Because you're picking on certain genetic characteristics that are expressed as phenotypes, and so that would cause selection. And then again, no natural selection. Okay, the environment is not choosing certain ones to be better able to survive. Everyone must have an equal chance of mating and reproducing and passing on those alleles. Okay, Hardy-Weinberg expressed these ideas in sort of a mathematical type formula in which they said p squared plus 2pq plus q squared equals 1 or 100%, where p squared is going to represent the frequency of the individuals in the population that are homozygous dominant. Okay, so p squared is going to be homozygous dominant. Okay, 2pq are going to be the percent or frequency of the individuals in the population that are heterozygous. And q squared is going to be the number of individuals in the population that are homozygous recessive. Okay, so these are genotypes of the ones in the population, and they should all equal 1, which is 100%. Okay, the allele frequencies, remember what we just did on that last slide. P is going to represent the dominant allele. Q is going to represent the recessive allele. So P plus Q is going to equal 100%. So big A is represented by P, and little a is represented by Q. So in that last slide, you remember that P equaled 0.70 or 70%, big A. Q was 0.30 or 30%. Okay, so we can go back and we could see if it matched, but P squared, you'd take 0.7 and square it, okay, which would equal 0.49. Q squared, which would be 0.3. You take 0.3 times 0.3, and you're going to get 0.09, which would be 9%. Okay, then you take 2pq. So 0.7 times 0.3 is 0.21. times 2 is 0.42. Okay, so if you do your math, what's 49% plus 42% plus 9%? Right, 1.0, okay, or 100%. And so kind of smart. They figured out that these allele frequencies, if you count up how many individuals, and oftentimes you're going to look for this one right here, how many individuals in the population are homozygous recessive, because if they're showing the recessive trait, then we know they have to be homozygous recessive. Okay, if they're showing the dominant trait, it could be either one of these two. Okay, it could be big A, or big A, little a. So if we can find out how many are recessive, showing the recessive trait in the population, we can take the square root of that. Okay, so if we know it's 9%, we can take the square root of 0.09, and that's going to give us our Q of 0.3. Once we know that, we can take 1 minus 0.3. That tells us P is 0.7. So now we know P and Q. We can figure out P squared, 2PQ, and we can go back and forth, and we can use this formula to figure out the frequencies of the populations. Now, if you look at those 5 things, like no migration, large population, no natural selection, random mating, does that happen in nature? Okay, very, very rarely. So that's why they would say this very rarely occurs in natural conditions. So that means, okay, so we'll say no. Okay, that means that there is probably evolution at some scale going on within that population, especially from mutations, non-random mating, and natural selection that's happening, especially if the environment is changing. Okay, so this is just kind of a start. We'll work more with this equation in class and try to work through it a little bit better. But just giving you this idea of how Darwin was sort of connected to Gregor Mendel and how we can apply natural selection to actual allele frequencies and some of the stuff that we learned in genetics.